Anyway, we have here semi-cone B, so this is C over 2, negative B, X and Y. So the left is the integral from negative B over 2 to B over 2 of delta pressure of X dx, right? And the delta pressure is P lower minus P upper. So if you get P lower from here, P upper from here, and subtract, the P infinity will go away and you'll get twice of this term. So this is twice rho U infinity phi x plus phi t. So if we substitute here, you will get the left periodic span as twice the rho integral U infinity partial phi partial t, and this is on the upper surface, this is on one surface. So partial phi partial t phi upper surface dx plus, if you're integrating partial phi partial x with respect to x, you get phi between the 2 points. So you get U infinity phi at the trailing edge minus phi at the leading edge. And remember that you have freedom to select phi at one point. The value of phi doesn't matter. The value of phi doesn't matter. What really matters here for the definition of phi is its derivative. Okay? So the derivative means that the changes of phi from one point to another, that really matters. So this means that you can assume phi at one point in the plane. Okay? Doesn't matter. So whenever you have a phi field, you can add a constant to the entire field. That's fine. So I'll assume phi leading edge for simplicity to be 0, and this is an expression for the lift. So as you can see here, to get the lift, get the unsteady lift, all what you need to get is what? It's just phi. So only need phi on the upper surface. Okay? So let's get phi. And to get phi, I will derive a relation for the mapping. So this is actually a side. And probably this is the last thing that we will do. It's quick and it's very intuitive. So you have your circle, and I will map this to here. And the mapping is known. Zeta plus radius squared over zeta. What's the radius? Well, if this is b and this is negative b, then the radius will be b over 2, correct? So radius squared is b squared over 4. Okay. On the plate I have here U and V. And on the cylinder I also have U and V, but it's convenient to do it as VR and V theta. Okay? What is the relation between these two components and these two components? This is coming from the mapping. I mean, if you got conformal mapping before, you should have learned it, but we will derive it very easily now, just to be self-contained. It's very easy. What is the complex potential, the complex velocity in the z domain over there? If you have a complex potential F, how you get the components here? dF by dz, right? How to relate it to the cylinder? Well, it's dF by d zeta divided by d zeta by dz, right? So in the z domain, this is u minus iv. In the cylinder domain, in the cylinder domain. This is also u minus IV in the cylinder domain. But if you want to relate it to VR and V theta, we have another relation that we wrote before. It's e to the negative I theta, VR minus IV theta, if you remember. Okay? And these z by d zeta, we can get it from this relation. It's 1 minus b squared over 4 zeta squared. Okay? So, u minus IV equals e to the negative I theta, VR minus IV theta divided by this green guy. But this green guy on the cylinder, what is zeta? Can you give me what's zeta on the cylinder? What's zeta on the cylinder here? Its radius, e to the I theta, correct? So here we have 1 minus, if you square this zeta, you'll have b squared over 4 goes away. And if you square this, this will be e to the 2I theta going up. So e to the negative 2I theta. Okay? Any question about that? So this guy will go here and make e to the I theta minus e to the negative I theta. And what is this? So the real part will cancel and the imaginary part will be 2I sine theta. And the I will go up. So I will have, I will go up, negative I times negative I is negative 1. So I'll have negative V theta over 2 sine theta. Like I said, the I will go up with negative I here. So negative I VR over 2 sine theta. And now you can compare. So immediately we get that the U is negative V theta over 2 sine theta. And the V is VR over 2 sine theta. Okay? So this is at any x on the plate, at any x on the plate, at any theta on the cylinder, theta on the cylinder. Okay? So we related, I mean, this makes sense. This is the tangential velocity on the plate, this is the tangential velocity on the cylinder, normal velocity on the plate, normal velocity on the cylinder. I mean, this makes sense. We could have, devised it from the get-go, but this is a formal derivation. So, having this form, phi at any x actually is the, maybe from the leading edge, is the integration from the leading edge to any x, partial phi, partial x, dx. Do you agree about that? This is partial phi, partial x is u. And we agreed to put this guy as 0. So this is the integration of u. We simply just said that u is negative v theta over 2 sine theta. Times dx, we still have the same relation. So x on the plate is d over 2 cosine theta. So if you differentiate to get dx, this is negative d over 2 sine theta d theta. And the leading edge is theta pi, any x theta here. So you can see that this guy goes away. And what else? I guess we're done here. So phi at any theta is the integral of, we have negative, we have b theta to pi v theta of any angle d theta. And we have, I guess we're missing 2. Is it over 4? I doubt this 4 thing, but let's see. Okay, now it's b over 2. There is 2 somewhere. I guess this is b only. Yeah. So, and just to prevent confusion, this is the tangential velocity at any angle. I will call this angle phi. You know, it's dummy variable of integration, but just to prevent confusion. So, towards our objective was the unsteady lift, and the unsteady lift, we were waiting for phi, the velocity potential. We just wrote phi in terms of the tangential velocity v theta, so now need v theta. Now you're gonna pick from here next time. Okay? Any question? Any question? So homework